Thanks for coming, folks. My name is Rob. This is us on Twitter. After the event, we will tweet out the slides and a bunch of links to some code that we've got. So if you want to get it, that's where it'll be. I work at a company called Basement Crowd, which is a legal tech startup with my colleague Sumanas. And over the last 12 to 18 months, we have been working in machine learning research, specifically around natural language processing, and named entity recognition and information retrieval. So doing a lot of stuff with legal documents, that kind of thing. So we're here today to talk a little bit about some of the stuff that we've learned doing this in a commercial setting, some of the challenges that we faced, and then the second half will be a couple of machine learning demos just to make it a bit more interesting for you, just for a bit of fun. The first half is going to be mostly quite soft stuff. It's not going to be very low-level technical, so you don't need to worry about knowing a lot of machine learning theory. So let's jump straight into it. Why should we care about the problem of doing machine learning in a commercial setting? So as you probably all know, there's a lot of hype around machine learning at the moment. It's a very big trend in the industry. You have a lot of the big tech companies really playing up the future promise of machine learning. The Google, Facebook, Amazon, all talking a lot about how important it's going to be now and in the future. So if you saw the recent Made by Google event, all of that was kind of about how they're building machine learning capabilities into all their products and all their hardware. And as well as the big companies, there's also a lot of hype in the press and amongst the analysts about how important it's going to be in the future. So the Accenture Technology Visions report this year said it's going to be a key differentiator for businesses. You've also got other people being a bit more serious about it, saying that any product that doesn't use machine learning or artificial intelligence will die, which seems a touch dramatic, but it gives you an idea of the hype around it. A more interesting thing was a Narrative Sciences survey that came out last year that said 62% of organizations surveyed plan to be using machine learning or artificial intelligence by 2018. So this is really an exciting number, because what this is saying is that 62% of the people they're talking to are planning to have machine learning teams and machine learning technology within their organization within the next 12 months. So that's quite a bold statement, I think. As well as the hype, we're starting to see meaningful numbers and meaningful change across the industry. So this year's Spectrum ranking of programming languages has put Python to the top. Now, obviously, ranking of programming languages is a bit of a dark art. It's a bit, finger in the air. You'll get a lot of different rankings. But Python has been on an upward trajectory for the last couple of years, which is undoubtedly driven in part by the machine learning community and their libraries. And then we've also got this year's Stack Overflow Developer Survey, which is a bit more concrete, and that put machine learning engineers as the second highest average salary. So we're starting to see this movement and this demand in the market around machine learning, and all the hype is saying this is just going to continue to grow. But of course, as well as all the hype and the excitement, there's a natural amount of skepticism and cynicism amongst analysts. Harvard Business Review said the first wave of corporate AI is doomed to fail, which isn't great if we're trying to do it in a corporate environment. A lot of comparisons are drawn here to the previous technological shifts we've seen over the last 2 decades. So in the 90s, the internet and the dot-com bubble that followed, and then in the establishment of a legitimate mobile platform. In both cases, you had companies and individuals rushing out to build websites and to build mobile apps when they didn't really need to. There's something of a gold rush. So people are predicting the same thing to happen to machine learning. Lots of companies rushing out to get involved because they feel they need to be seen in that space. So what can we do if we're trying to do this in a commercial setting? Hopefully this will be the main takeaway, or one of the main takeaways from the first half of the talk. And that is, we should approach it like we do any other product engineering problem. There really isn't that much unique challenges doing machine learning. And so I'm going to talk through a couple of product management principles and a couple of engineering principles that we can apply when we're thinking about doing machine learning in a commercial setting. So I'll start going through the product management principles first. I'm going to cover 3 kind of guiding principles. And these are kind of things that we came across whilst we were trying to build our machine learning and build our products, new products to take to market. So the first point is hopefully an obvious one to everyone, and that is machine learning is not a product. Machine learning isn't your product. So don't go out and build machine learning for the sake of building machine learning, okay? So customers don't want to buy machine learning. Customers want to buy self-driving cars, or they want to buy better voice controls for their home systems. They don't care about the magic flower, they just want to be Super Mario, okay? So that's the first thing. So make sure you have a valid product that you're trying to build, that you think is a legitimate product in its own right. The second principle, or the second question you should ask yourself when you're starting on this journey is machine learning part of my minimum viable product? So in a lot of cases, the answer to this is going to be no. If you're building a brand new product, the first thing you want to do with your minimum viable product, your MVP, is to try and verify your product market fit. You want to make sure that customers are willing to pay for this idea that you have. And if you can verify that and you can take it to market without actually having to pay the cost of building a machine learning team and building out all the infrastructure around that, then you're de-risking it quite a lot. Because it might be that you take it to market without the machine learning. So maybe you've got a team of people extracting data manually, which would be replaced with machine learning if it's a successful product. And you take it to market and then nobody wants to buy it. And if you haven't invested in the machine learning, then you've not wasted so much money. The third question is your machine learning mission critical? So an example of where the answer would be yes would of course be self-driving cars. So your machine learning model, if you're building a self-driving car, is absolutely mission critical. You have to be sure that your machine learning and all the infrastructure and all the rest of the pipeline around that is really solid. It needs to be performing really well before it can even go near customer testing. Okay? But for those of us who aren't building self-driving cars, there's probably lots of scenarios whereby we don't actually need to worry about getting it perfect. So if you take, for example, let's say you're building Instagram or a photo upload service, and you want to have some machine learning that's going to automatically suggest tags to a user when they upload a photo based on what the model thinks is in the photo. Now in this scenario, I would say this isn't mission critical, because the user could upload it, and even if they're only suggesting 2 out of 4 accurate tags, so the other 2 are just nonsense, so a 50% accuracy rate, you can already start to add value to the customer. So you could potentially start to roll out a poorer performing model and start to get value from the customer. You also get insights and additional data to put back into your model to continue to train and to improve the performance. And it means you get to test the infrastructure and the pipeline and all the deployment stuff around it. So again, this process of asking this question is a way of de-risking your machine learning investment. So to recap these three principles. Firstly, have you got a product in itself? Okay, if you say yes, do we need to build machine learning for a minimum viable product? And then thirdly, once you've got product market fit and you're happy with your minimum viable product, you can say, is it mission critical, or can we start to roll out and incrementally build on this? So if we follow these 3 principles as we're building out our machine learning, then the goal is to de-risk everything and to reduce the chance of us being a failure. So those are the machine learning principles. Product management principles. Now a couple of comments on engineering and engineering best practices you can do. So once again, same theme as the last one. It's still just engineering. So we apply the same good practice you would apply to any software product that you're building, okay? And it might seem strange coming to a developer conference and saying, clean code and testing and modularity. These are things we will have heard lots of times for many years. But the difference with machine learning is there will be a lot of time where you might have a team of researchers who might not necessarily have an engineering mindset, but also, more importantly, even if it is engineers, there's going to be a lot of experiments going on. You're likely going to have your team doing a lot of research quite open-endedly for a period at the start. And when you're doing research and experiments, a very natural tendency is just to hack something out. You wake up in the middle of the night and you have an idea of what you can do. You don't want to come in and start building out all the the best practice and the clean code and all this kind of stuff. You just want to hack out a script and see if it works. But really, you need to approach it with an engineering mindset from the start and make sure you have your researchers and your engineers working together to try and ensure this. As we'll see in a minute as well, in a machine learning pipeline, actually only a very small part of it is machine learning training and prediction. There's a lot of other code around the periphery which does data cleanup, data collection, verification, testing, monitoring. So you've got all these other components which absolutely should be reused components you can use across experiments. They should be tested. That way then when you have multiple experiments going on at the same time, you save time and you have the confidence that they're being benchmarked against the same level and against each other. Oh, too far. As well as those engineering best practices, there are also some specific machine learning patterns or anti-patterns. This is taken from a paper called The Hidden Technical Debt in Machine Learning Systems. If you're thinking about running a machine learning team, I absolutely recommend everyone on the team reads that. It's not too long, and it covers a lot of machine learning anti-patterns and code smells and some of the challenges you can face. So you can see here in this kind of representative picture, this is what they're saying is your actual machine learning code. Everything else going on here is kind of normal engineering code. In that paper, they also identified several anti-patterns. Dead experiment code is exactly what it sounds like. So for those of you who are in the keynote this morning and heard the example about the trading company that lost everything in 45 minutes because they didn't delete code, that's exactly what that is. Configuration debt is about actually in machine learning, there's an awful lot of configuration, and actually a large part of your overall pipeline can be configuration. So it's the importance of making that manageable, testable, and easily changeable. And then we have code glue and pipeline jungles. And these are concepts that are all about how you build out your pipeline and the tendency for them to become over complex or for people to just drop in kind of ad hoc bits here and there. So you might be running your pipeline and then you realize, oh, I need to do a little bit more data manipulation before I run it in. So I'll just chuck in some code into the script and it'll just clean up the text or it'll trim something. And actually, also from that same paper, there you go. So this quote's from that same paper. And I think this is kind of reinforces the point I'm making, which is glue code and pipeline jungles are symptomatic of integration issues that may have a root cause in overly separated research and engineering roles. So again, it's really important that your researchers are approaching it with an engineering mindset and that they're really working closely together. If you even separate them at all, you can have obviously engineers doing the research, which is great. So the final bit of this soft stuff at the start is the agile thinking for it, and how can we do all these things within a commercial environment where you have agile development teams and you might have management who have expectations about things being delivered. It can be a challenge. So one of the things that we found useful was the concept of research sprints. So our normal development team work in fortnightly development sprints. And what we found useful was to tie in the research sprints into these development sprints. So at the start of the sprint, your researchers have a hypothesis that they want to prove or they want to test. And then they spend that sprint, maybe not the entire time, researching it and trying out this experiment. The goal being at the end of the sprint to have a go, no-go decision as to whether or not it's worth continuing or whether it should just be abandoned and thrown away at that point. You get a couple of benefits from tying it together. You get this closer communication and transparency between your development and research team. You also get some cool demos at the end of the sprint, especially when things go wrong. It's good fun seeing cool machine learning stuff. And also, you get clear checkpoints to make sure you kill off not entirely productive research avenues early on. Because with research, it's very easy to always have a little bit of hope and to keep on plugging away, whereas with this, you can kind of kill it and just move on. Also, and hopefully this will be more obvious when you start to work with machine learning, but borrowing from Eric Ries's, the lean startup, lean engineering principles, this build, measure, learn cycle is really important. Obviously, you need to be always measuring in most things, but if you're not measuring, you can't improve things. And going back to the mission critical example earlier, you can think about, you don't need to go straight into using something overly complicated. So there's a lot of hype and fanfare around Google's TensorFlow at the moment. It's a very cool thing to use. People are going to want to use it, but given your problem, it might not be right. There are probably lots of other options you can pursue, first of all. So what we did, we were working on a lot of data extraction, named entity recognition from documents, and we kind of went through these processes of using simple rule-based stuff. Can we use regular expressions? Can we use hard-coded rules? Also looking at traditional off-the-shelf libraries. So Stanford have got a natural language processing library in Java, and Apache have got one called OpenNLP. And both of them perform really well at some tasks, and with some configuration and training, you can get good results out of them. And then you can iterate, if you need to, onto a more complicated deep learning TensorFlow style pipeline. So those are the kind of the soft principles that we've kind of learned, and we try to apply when we're working in a commercial setting with expectations about delivering things in machine learning. I'm going to hand over to Sumanas right now, and he is going to show you some stuff which is a lot more fun. So, Sumanas.
Hi, so I think you start with good news, everyone, if you're Futurama fans. Basically, the main thing that I'm trying to do with the machine learning side is, while Rob's covered all the agile side of things, the management side of things, so to speak, I wanted to go a little bit into detail of text processing and specifically natural language processing for machine learning, which is what we've been doing at Basement Crowd. I appreciate that this is not a machine learning conference, so you're not going to see equations, you're not going to see complicated formulae with gibberish to me also sometimes, so this is going to be very high level, and I will skim over some stuff. Please catch me after the talk if you have any questions, you want to know more about it, I'll do my best to explain it to you. So getting down to the basics of it, the computer can't understand text in the way these machine learning algorithms work. You can't just feed a sentence. So if you take, this is a 6-word sentence, AI pretends to fail Turing test. Say you want to do some classification on this. You want to do sentiment analysis, you want to tag nouns, verbs, adverbs, you want to detect all sorts of different things from it. For the machine learning algorithms that we want to try, you can't really feed it the text. You want to encode it as numbers. You need to have a numeric representation of the text before you can really start doing anything. And it's critical that this step is explored well. A lot of machine learning pipelines just skim over this initial step and run straight to trying out all these cool new algorithms and all these cool new things. Like this month it might be support vector machines, next month it might be random forest, and they're all eager to try it and see if that gives them a better result. Ultimately, if your encoding is poor, no matter how good a machine learning model you have, it's probably not going to do well. If you have a very good encoding, a basic model, it's going to do fantastic most of the times. So a very basic one is you just assign a number to each word. It's pretty obvious in retrospect. but basically it's the word AI gets the number 3, pretends it becomes 145, and so on. And you maintain a list of, say, the most commonly used 1,000 words, most commonly used 10,000 words, depending on the variety of words used in your problem domain, how large it is, how much memory you have available. It may be maybe you want 1,000,000 words, but you don't have enough RAM on your servers to deal with it. So it's really about the problem that you're facing, and you have to tailor it to that. So this particular encoding is very simple, it's very basic, and it's quite powerful. It's called Bag of Words. There's a Wikipedia article, please read it. It's a fundamental starting point, and it will give you some very basic results that you can give you an idea of whether this is worthwhile proceeding with it or not. So we restarted with this, and we realized that we needed something a little more powerful. So we replaced it with Word2Vec. So Word2Vec is this encoding format that instead of going from one word to one number, now each word is represented by an array of numbers. The dimension of the array is again a configuration parameter, and you can have 10, 100, 300, 1,000. It depends again on your problem domain. You have to try different numbers, look at existing research to see what other people are doing with similar sets. I think Google, where this is from, they have a 300 dimension array for each word. It works for them. You don't have to use 300. You can do very good stuff at 50 or 100. So now what happens is each of these words gets encoded as an array, and the dimensions are the same. So now, hopefully, you're beginning to see that it's becoming a bit like a matrix where you have 6 rows and either 300 columns, 10 columns, 1,000 columns, depending on what dimension you've chosen. And this allows us a little more granularity in how we're representing the words. Because instead of having that one number, you get a little more degrees of freedom. It's almost like coordinates. You have like an x coordinate, a y coordinate, a z coordinate, if you have 3 dimensions. With the numeric system now, you can actually go one step further. What if I wanted to represent this sentence with one array? So I have basically 6 arrays for 6 words. What if I want one array to represent the whole word? I can just take the average. I go column-wise, pick up the averages, and I can get a mean of, so to speak, of the whole sentence. And now suddenly I have a representation, a numeric representation of the sentence. I can go a step further and say, every sentence in a paragraph, I have a numeric representation of the paragraph. Go a step further, all the paragraphs, pages in a document, a whole document. So this is a very powerful and very simple system. People have improved on it. One of the downsides is the word AI will have only one mapping. So this is one of the downsides, that if you think of a word like bank, it has many different meanings. Do you mean a riverbank? Do you mean as a noun? Do you mean as a verb, the banking of an airplane or a bird? Or maybe you mean a bank as a banking organization. The Word2Vec is just going to give you one same array each time. So there are iterations on this, which I'm not going to go into now, but if you want, please read about it, and it has details on how to deal with these situations, but you should only go into them if you find that this is not giving you good results. It's always keep it simple and only add complexity if you find that you're not getting the results you need. And now, I'm going to try and do some live demos. Hopefully, nothing goes horribly wrong. Because, you know, what could possibly go wrong with a live demo? Okay, so one of the things is word algebra. It's very basic. Maybe you've seen it before if you have any interest in this field. It's the idea that if I have each word represented, then I can start doing some very basic arithmetic with the words. So let's say I take quill, the word quill, and I want to, so I just add the word quill, and I add ink. So what happens if to the word ink, to the word quill, I add the concept of ink? And if we add these two together, the model tells us you get a pen. Now, this is a bit confusing for people who aren't used to thinking with words as vectors, so to speak, but it's actually quite powerful. What's happening here is that you take where quill is, so the blue dot on the left, over here, and you have an x and y coordinate, and then you have the word ink, and you have another x and y coordinate, and you can treat them as vectors, and you add them together, and you get your pen. Now what's really going on is, I'm oversimplifying this a lot because I don't want to go into the details, but essentially you add these two coordinates together, and you look at the resultant coordinate system, and you say, do a reverse lookup and tell me what word is closest to these coordinates, and it just so happens that the word is pen. And this has happened using the word-to-vec model, which learns these representations of our words. Another little more probably fun example would be, let's say we take a banana, and I say, what happens if I want the vegetable equivalent of a banana? What would that be? I mean, it's an interesting thing to think about. Like, how would you think about a vegetable equivalent of a banana? Well, thanks to this, we can actually give it a try. So we say banana, we add a vegetable, the concept of vegetable to it, and it gives yam. But you might say, okay, it's not good enough. I want to play with it a little, and I'm going to now remove the concept of a fruit. So it's like a pure vegetable, because now we've got like a vegetable and a fruit mixed together. So if you subtract, you get a plantain, which I think is pretty neat. If you look up what plantain is, it's pretty much a vegetable equivalent. And again, all that's happened is, I'm trying to show this with the graph over here, is that you have the banana and you have your x and y coordinates there. You have a vegetable with its own x and y coordinates. You add them together, but you subtract these x and y coordinates, and you end up with these. And it's just done a reverse lookup to find the word that's closest to those coordinates, and it just happens to be plantain. You train the model differently, you'll get a different result. So if I, for example, train this model on Shakespeare, I'm not going to get plantain, I'm going to get something else. It just so happens that I've trained this model on Wikipedia and some legal text and some books from Gutenberg. So it's got a bit of a mix of everything in there. But for your domain, you find a text that's specific to what you're doing. So if you have customer manuals, you just feed the model customer manuals, and it will get very good, and you get a completely different result for this. It's specific to the model that you use. So a final word algebra demo that I want to try out is something which I found when I was dealing with Gutenberg was you can actually do some pretty cool stuff with characters in fiction. So if I take Batman, right, and woman, I get a weird result, all right, and I want to remove man from this. It gives me Catwoman. Now, this could be, this is a very interesting example, because it could be that there's not many talks or literature about Batgirl in the text that I fed the model. That's why it's saying Catwoman, because it's seen a lot of Catwoman. What the model doesn't know, just like us, it does not know what it has not seen. So these become your frames of reference for checking. So you maintain a list of, when you're training these things, you maintain a list of these challenges that you would hit the model with to check how it performs. And then when you have different configurations, like you might say, all right, I'll take, this might be with, so this is with 300. So I've got 300, an ordered list of 300 words for every single word in the vocabulary, which is, I think, for this model, 84,000 words. The Google one is over 1 billion. You can just download the trained model from their website, and it does equally well, but that's sort of like a general tool. If you don't get good results with that, train your own one. So this is with the individual words. It's cool and it's fun to show off with at the end of a sprint. Everyone oohs and ahs, and suddenly, all the engineers want to talk to you. But is it what can you do with this? Surely there's more that you can do with this. So one of the things is, as I told you, that you can average out sentences, you can average out paragraphs, you can average out whole documents. So what I did is I scraped IMSDB. For people who don't know, that's you know about IMDb, which is the Internet Movie Database. IMSDB is the same thing, but with scripts, so movie scripts. So I scraped about 1,500 movies and put their scripts through this. Now I have a numeric representation of every single movie script. And that can be now visualized using TenSupport. So TenSupport is a tool that you get with TensorFlow. I've not actually used TensorFlow at any step here. It's just I'm using the TensorBoard visualization system. And each blue dot here represents a movie. And it's immediately apparent that there are clusters forming. So that's Great Expectations. You get all sorts of different things. You have these little clusters forming to one side. That means that there's some similarity between these things on one side. And these are like Futurama episodes. So these are TV episodes. There's a few handful of them, but it's, the script is substantially different enough that the coordinates are off to one side, forming their own little island. You've got Last of the Mohicans, The Patriot. So, what happens if I put in Star Wars? You get all the Star Wars films, well, all of the ones that are on there. You have the 6 of them that IMSDB has. And it should be obvious to some people now that there is a fundamental difference in the scripts for The Phantom Menace and Attack of the Clones that separates it from the other films, and it's right up there. They're very close together, but Phantom Menace and Attack of the Clones are off to one side over here, and you've got Star Wars, and Transformers the movie apparently is also very close to it. So this starts to get a little more useful. You're going from cool and fun to something that can actually be used somehow, and maybe even start thinking about a business use for this. So one of the ideas that I had was, what if we started recommending movies? So normal movie recommendation systems work using star ratings, or finding other people who like this film, so you would also like this film. Who directed it, who starred in it, when did it come out, what's the genre, all these different things, but we never actually look at the film itself. So right now, I can say, if you like this Star Wars film, these other films in the coordinate space are very close to it, so maybe you want to have a look at them as well. And it becomes a content-based recommendation system, not metadata-based recommendation system, which can be quite powerful. So that's when we moved on to our proper demo or proper MVP sort of situation. And so you enter a movie title. Let's try Die Hard, and I really hope the demo works now after all of this. Okay, so you get Die Hard 2, Manchurian Candidate, True Lies. This is pretty cool. You're getting recommendations of movies based on the script of the film and how close it is to the movie that you specified. So now I can click on Die Hard 2, and obviously Die Hard comes up, but I get these other films coming up as well. One thing that I discovered using this was if you put in Total Recall, this is the film with Arnie in it, not the remake. You get these films, and I don't know how many people have seen this one at the bottom. The craning of necks. Adventures of Buckaroo Banzai Across the Eighth Dimension. So I'd never heard of this film, and apparently it's like one of the cult successes where it didn't do so well when it came out, but then everyone likes it. It's got some really famous people in it, Christopher Lloyd, Peter Weller, and it's about this neurosurgeon rock star who goes across galaxies saving the universe. It's a really good find. I'm going to watch it because it looks really interesting. And I also thought I would identify certain things you need to be careful of, because it's all, this is all really great, but there are limitations to this, and you must have someone overseeing it. You cannot just put this up and expose it without any oversight to your customers or the end users. One example where it can go horribly wrong if you don't do this is Aladdin. So if I ask for Aladdin, I get Shrek the Third, Shrek, Legend, and then Austin Powers, Bad Santa. That's not really good, is it? If you look at the vector space using the visualization, you realize that what's happened is that Shrek and Shrek the Third are quite close to Aladdin, but Austin Powers is a little further away, and it's just that we don't have any films that are close enough. And so the algorithm's just gone out and said, oh, what's the nearest neighbor to Aladdin? Oh, it's these two. And then I'll go a little further out and I find it. So you look at this as an example and you say, oh, we need to introduce a cutoff that if the movie is further apart from certain distance, and you use the cosine distance as a metric, for example. You can use Euclidean distance. There's, try out different things, and you use that as a cutoff for saying, oh, we're going to ignore anything that's more than this distance apart from the original film because it's of no use to us. And you can avoid things like this, but you have to have manual oversight. You don't want to expose people without knowing, because you tried on a handful of things, it worked great, what could possibly go wrong? And I think that's it.
Do you want to jump back then?
Yeah, and now it's over to Rob to finish off with the presentation.
Awesome. Yeah, I love Word2Vec. I think that's just so cool. You can just give it any amount of text and it just works it all out. I think that's incredible. So anyways, back to the drier stuff again, I'm afraid. We're not going to get into the discussion as to what language you should use to do it. As you can see, there are obviously lots of libraries and lots of languages you can use for building machine learning. TensorFlow being Google's very popular Python deep learning option. You've got deep learning for J, which is a JVM based deep learning thing, and you've got Spark. There's a whole host of things. But when it comes to choosing what you need to use or what you want to use, you just, like you would any other technology choice, you look at the team you have, you look at the hiring pool, and you look at your existing technology stack. And that's what should be really informing your choice, rather than just going out and saying, TensorFlow is cool, let's do that. Again, the recurring theme from the first half of the talk is really most of these things we should just be doing what we would be doing if it was machine learning. So don't get distracted by the fact that there's all these other fancy things. So modern architecture, cloud deployment, microservices, that kind of thing actually makes machine learning deployment relatively easy, relatively. So obviously containers makes it, if you're already using containers and Docker for your deployment, it actually makes it very easy to drop in a tech agnostic fashion, your machine learning components to interact with the rest of your deployment. So this is taken directly from the TensorFlow documentation. But again, whilst it's specifically about training machine learning model, if you kind of squint your eyes, you can kind of see it looks very familiar to existing engineering processes. So you have this continuous training pipeline now, where you have your data and you have a repeatable training process that's producing artifacts, which are your models. And then over here you have the serving, which is the deployment element. And Google have got something called TensorFlow serving, which enables you to serve up your TensorFlow models quite easily. So you can put that inside a container, and then you can just request whatever you need to ask of it. By default, it uses gRPC, but obviously you can wrap it in HTTP requests. You could have any kind of messaging service between the two. I think whilst it's all relatively straightforward in terms of we're still just deploying Docker or containers, or we're fits into our existing deployment process quite nicely. You will still have challenges because not many people have productionized TensorFlow or machine learning. So whilst the deployment is quite easy, building your Docker images might leave you scrambling around a little bit. You have to be reading some documentation or even source code. With TensorFlow, we ended up having to use Google's internal Bazel build tool and reading all sorts of source code to build just images of basic TensorFlow. So it's a bit of a challenge getting through without so much documentation, but it's possible. So this is really just to illustrate that point of containers and modern microservice type deployment stuff. So as you can see, you might be able to work out that this is the demo that Sumanas just demoed, and as you can probably work out, this is incredibly over-engineered. And we did that intentionally, just to kind of emphasize the point of the container stuff. So each of these blue things is a Docker container. We're using Spring Boot and the Netflix microservice open source stack. So we've got all this over-engineered service registry stuff. And then you can see down here, this is the service that does our recommendation based on the clustering using deep learning for J. But you could absolutely have another container down here, which is TensorFlow, and just interacting with it, or you could use any other of the machine learning libraries available. So it'll fit in quite agnostic of what's doing the machine learning aspect. So, like I said, the takeaway is really, if we apply the same principles we would if we were working hard on any engineering software product, then there's no reason we can't be successful also building out our machine learning products. So that's it. Thank you.